question is, in which direction is the bus going?
It isn't going anywhere. It's staying still.
Well,
It's going to my right.
Yeah.
While that may be an interesting trick answer to the question, we will assume that it is going. Okay, physics is a lot like this problem. Oh no, y'all want to drop.
We got a 50 now.
While it is fun, it is sometimes frustrating until you see something you hadn't seen before. Or in this case, notice something that should be there but isn't in this case, right? Where's the door at? Okay? So, once you get the one connection most of the time in physics, or connect it to something, physics usually, the light bulb goes on in your brain and it becomes a much, much easier course. Now, until you get to that spot, sometimes it can be kind of frustrating and you don't know which way your bus is going. All right? So, hang in there. All right? You can get it and you will. All right? So, we've talked about energy a bit already. We're going to talk more about energy today.
I would have a whole lot more if I had some food. Energy, that is.
Me too. All right. You shall have your chemical potential energy at
Hey, look.
A line. Quarter after, right?
Yeah.
Wait, what?
Yeah, see that?
We've seen.
We have C line.
I had 12. But they just say that offers instead to go to A lunch because
Nope.
I didn't check it.
All right. We are going to talk about more about energy today. All right. Okay. Last time we started talking about potential or different types of energy, right? And so what we came up with? We came up with kinetic, which is energy of motion. Okay? We had potential, which is stored energy. Okay? I want you to write this down next to potential energy. I want you to write down
Gravitational.
that it comes from conservative forces. Okay? Potential energy comes from conservative forces. And we'll talk about what that means in a little bit. Okay? All right, and of potential energies, we had several varieties, right? We had gravitational,
Elastic and electrostatic.
elastic, or spring, and electrostatic. Those will be the biggies we'll deal with here. All right, and then we had thermal, or internal. All right? And we learned that thermal or internal energy is unique amongst the types of energies, right? That it is a random energy. Okay? All right. And thermal energy comes from dissipative forces. Okay?
Can I switch chairs?
What's up?
Can I switch chairs? It's squeaky.
All right? Thermal energy comes from dissipative forces. And we'll talk about what those are. Okay? All right. The types of forces that create those, as opposed to the types of forces that create potential energy. All right? Okay. Let's tackle them. Let's tackle them one at a time as we go through here. All right. So, kinetic energy. That was my question. taking badge. I'm gonna steal your badge. Want your badge taken. All right. Kinetic energy is the energy of motion. Now, when we talk about kinetic energy, remember we're talking about all the atoms, all the molecules in the object moving together someplace, all right, with a certain velocity. Now, this is translational kinetic energy, okay? Moving from one place, translating from one place to another. There's actually another type of kinetic energy. It's called rotational. And that's 1/2 I omega squared. Now we will talk about that one when we get to Physics C. But I just want you to know that there is two types of kinetic energy. The type of kinetic energy of when you move from one place to another place. And then there's the type of kinetic energy when overall your atoms are not moving from one place to a new place, but they are rotating. Okay? So like the Earth has translational kinetic energy because it's in orbit. It's moving around, right? And the Earth has rotational kinetic energy because it spins on its axis, right? So it's possible to have both at the same time, okay? So, just so that you know, all right, does anybody know what omega means? Have you learned that anywhere? What's omega?
Ohms.
Yeah, it is a Greek letter. It's the Greek letter omega. It's the small omega, not the big omega, not this omega. All right, which means ohms, right? Now this is the little omega.
That is.
All right, so that's okay. You don't know. Omega means rotational motion. It means rotational velocity or angular velocities. Like for instance, this velocity means meters per second. That's its units. So something, you start here and you end up over here, and the change in distance over the change in time, that's your velocity, right? Or for those of you that have had calculus, that's dx dt, right?
Yes, sir.
All right, so your velocity is your rate change of position or your location. Okay, omega on the other hand is your radians per second. Okay, now what the heck's a radian again? It's an angular measure, right? It's an angular measure of displacement. Okay, all right. Do you know why in physics we don't use radians and we use degrees? It's because we've grown up with degrees, and so we've memorized degrees, so we use degrees. That's why. Because if I ask everybody to give me, how big's a 45-degree angle? 45 degrees. Half of 90. What's 90? That, right? So 45 is like that, right? So if I gave you, what's 135? Okay, everybody, pantomime. What's 135? Okay, because 180 is this way, right? 90, 45, 30, 135 would be somewhere over here, right? Okay, if we go beyond 80, it starts to get a little more complicated, right? If we go beyond 180, okay, but we can pretty easily, most of us, get angles from 0 to 180, not a big deal. We can figure it out, especially 0 to 90, piece of cake, right? And that's a really bizarre numbering system, right? 360 for a circle. They actually tried to change that at one time into a unit called a gradient, which was, I believe, a circle split up into 400, because that way a 90-degree angle would now be broken up into 100 segments instead of 90. So you go 100 in each quadrant. But nobody liked it, okay? All right, same reason that we have stuck with miles per hour and ounces and pints and quarts and gallons and all that stuff in America instead of going to the metric system is because we've grown up with it and we're familiar with it. All right? So that's the only reason why we use degrees. It's just because we like them. It's what we've learned. Radians, on the other hand, are harder for most people to figure out. Like if I asked you what's 1.6 radians?
Yeah, that's about 90 degrees.
Yeah, and you can figure it out, but it's not as fast, right? Okay, so that's why we use degrees. But anyway, radians is our standard unit of measure for angular displacement in math. Okay, so a radian per second gives you how far the thing has rotated in a certain amount of time. Okay, so instead of this translating,
But we still use radians per second, not degrees per second for that?
we will use, when you get to physics C, we can use both.
Because it's calculus based, so you use radians and calculus.
Right. When we do the math of it, it's much easier to do it in radians. But when we think about it, it's much easier to think of it in degrees. But when we talk about angular motion, we generally will talk radians. Okay? All right. Now the difference between translational velocity and rotational velocity would be, you know, the object, instead of translating, it rotates. So rotates. Okay? All right. All right, now, just a heads up for when you get to Physics C, that we will investigate this. So rotational motion is how fast you're rotating, and this I takes the place of mass. It's like the rotational mass. It's called moment of inertia. Okay, so everybody real quick stand up. All right, give yourself a little room so you don't whack the next person next to you. Stick your arms out. Okay, and go like this. All right, crack your back. Okay, feel how much torque you have to apply to make that happen. Okay, now bring your arms in and do the same thing. Is it easier or harder? Wait a minute, why is it easier to do this than it is to do this?
Because your arms are going further. They're going further when they're out here.
Because think about where your mass is located, right? When you're like this, your mass is all along your axis of rotation, and so it's easier to rotate it. All right. When they're way out here, your mass is located farther out. Now, all of the physics that we're going to do in Physics B is going to assume that all of your mass, whatever you are, whatever your shape is, that all of your mass is just in one spot, just at your center of mass. And we won't care how big you are or how far your mass is spread out. So like when somebody flies through the air, if we launch them through the air, all we're really tracking is this one spot when they go through the air. Not their feet, not their head, not their arms. Their arms may be flailing, they just jumped off the high dive, but they're in a nice parabolic motion because their center of mass is following that spot. Only that spot. Does that make sense? Okay, what happens to the rest of their body when they rotate, we start taking that into account when we get into Physics C. All right? So everybody can have C. All right, so this is for Physics C, so we're going to cross that one out for right now. Okay, you'll get to this when you get to Physics C, but I just wanted you to be aware of the fact that there are more types of kinetic energy than just translational. There's translational and rotational, but we're only going to talk about the translational in this class, okay? All right. So, physics is the study of, really, fewer and fewer lies. All right? What we do is we tell you what the world would be like if there's no friction and no air resistance, right? What the perfect world would be like in that case, the physics world. And then we add more and more and more things onto it with the same ideas, and we apply it to more complicated situations as we move outward from the center. Okay? So we're going to avoid this one for now. All right, so gravitational. Remember we had that last time and we broke that into two sections, right? There is gravitational potential energy in general, which is minus big G m1 m2 over r squared. And we have gravitational potential energy if you're near the Earth's surface or near the surface of a planet where the gravitational force doesn't vary much. Yes, ma'am?
Last time you wrote that and then you said it was all.
Oh, I did it again, didn't I? Thank you. This is r, not r squared. I did it again. Thank you for keeping me on track there. mgh here, okay? So if we're talking about planets or astronauts, we'd use this one. If we're talking about on Earth, or unless unless they tell you otherwise, we'll use this one, okay? Where G equals, what's G equal, you remember? 9.8 meters per second squared, which way? Downward. Now, I'm not going to put negative on there because it depends on which way you call positive. So it could be positive or negative. We just know it's going to be downward, okay? All right, so there we go. 9.8 meters per second squared. That's the acceleration due to gravity, or because of gravity. All right, elastic potential energy again is, for a spring, it's 1/2 kx squared, right?
Yes.
All right, so we'll talk about that one in just a minute. And electrostatic is K Q1 Q2 over R. I'm going to have you write it another way as well, a way you probably didn't see it last year, which is 1 over 4 pi epsilon naught Q1 Q2 over R. Okay, just write it down. Don't ask any questions yet. Difference between these two is what? Yeah. So this right here and this right here, they have to be the exact same thing, right? Okay. So this is the more basic way to write it. This is the simpler way to write it. Guess what? K and this thing right here, 1 over 4 pi epsilon naught, they are mathematically the exact same number. They're just a constant, okay? And we'll talk about that in just a minute. All right. So there are our major equations. Thermal energy we're going to get to in a little bit. We'll cover that a little bit more later. You've got that bus we were just looking at. Our nice, crazy looking bus.
Flintstone wheels.
So we know you're not an artist.
Okay, so see, your grade's going to be interesting. All right, say if this bus has a mass of, I don't know, 5,000 kilograms and is moving to the right at 10 meters per second. Okay, so that bus going that way, or what if we have the exact same bus going this way? Because we could never decide which way it's supposed to go. All right, so same bus going that way or this way. When does it have more kinetic energy?
Whenever it's going either,
It's
whatever
going
you find is possible.
Both of them has the same amount of kinetic energy. Either way.
The magnitude is the same, but
Will the magnitude be the same of the kinetic energy?
Yes.
Will they both be the same kinetic energy? 1/2 mv squared. Will they be exactly the same?
Yes.
Yeah, because what happens is the plus or minus, direction-wise, if we call to the right positive, which we normally will, we call to the right positive, then this one's positive and this one's negative, but when you plug them in, they're going to be squared, so it's going to be positive either way, right? So it won't make any difference. Okay, it also doesn't make a difference philosophically, because the concept of energy is a scalar. Okay, do y'all remember, or have you heard of what a scalar is? What is a scalar?
It's just a number without a direction.
Yeah, it's a number without a direction. I want you to start thinking of it as a scalar is something that has a magnitude and a unit. Okay, the magnitude tells you how big, and the unit tells you how big of what. Okay, so like if I tell you 10, is that $10? Is that 10 miles per hour? What is it? Okay, so you need to put a unit on things. So when you write down any kind of answer, you need to write down the magnitude and a unit every time. All right? Now there are a few numbers in this class that are unitless, but most of them will have a unit. Okay? All right, magnitude and a unit. Now that is different than if you have something that's called a vector. A vector has a magnitude and a unit, so it has a magnitude telling you how big, but it also has a direction associated with it, right? Okay, kinetic energy, even though we kind of think of kinetic energy as maybe vector-ish because it's moving in one direction or another, in reality, kinetic energy is a scalar, meaning that it doesn't matter which way you go. So if you're going towards Dallas or if you're going towards Fort Worth in a car at the same speed, it's the same kinetic energy. It doesn't matter, okay? Because all we have is magnitude and a unit. Magnitude, but no direction, okay? All right, so that makes life nice in the concept of work and energy. All right? Because if you have scalars, scalar math is just going to be plus, minus, multiply, divide for the most part. There'll be a little bit of sine or cosine in it, maybe, but it's just going to be regular math. Now, if you have vectors, the math is different. Like, for instance, you remember the difference of when you have forces. When you have a force this way, pulling something across the ground. Okay? Force is a vector idea. And if it's a vector idea, then you have to handle it with vector math. And vector math will be trig. Okay? So you have to break this thing up into its x component and its y component, right? And you have to work all through all the trig stuff. So use geometry math and trig math, right? Up here we use just regular old algebra. Nice and easy. Okay? So when we're in energy, the math will be much simpler. All right. Questions? You doing okay?
Yes, sir.
All right. Not your brain's training so far. Okay. Let's talk about stored energy. So kinetic energy is the energy of motion. It's really easy to find. 1F mv squared. Piece of cake. And that v is not the x velocity. It's not the y velocity. It is the total velocity of the object. All right? Okay. Let's talk about all these stored energies. Okay. Potential energy is stored energy, and these come about from special types of forces, okay? There are only certain potential energies, and they come about because of the work done by what we call conservative forces, okay? So let's get our list of conservative forces. Versus things like dissipative forces. Okay? The key thing that makes a force what we call a conservative force is if the force depends on location. Okay? Like, for instance, gravity. Okay? Gravity force, F sub big G here, is equal to, it's technically negative big G m1 m2 over r squared. Okay? There's that, and the square is right on this one. Okay? Alright, so gravity depends on location. So like, for instance, when we're on the Earth's surface, okay? Here's the Earth, it has a mass. Here's us, we have a mass.
Is it really r squared this time?
It really is r squared this time. This one's r, this one's r squared. I'll show you why in just a minute. Okay? Now, this is potential energy, this is the force. They are different. All right, so what's the radius between the Earth and you?
0, most likely.
Yeah, it looks like 0.
Or actually until the center of the Earth.
Okay, now remember we talked about in this physics class, Physics B, everything's, unless otherwise stated, it has to do with center of mass to center of mass, right? So where's your center of mass? Well, somewhere here. Where's the Earth's center of mass? Well, somewhere down here. The center of mass symbol looks like the BMW symbol. Okay? All right, so that's the radius in between the two of you. Now, this distance from your feet to your center of mass and the distance from the center of the Earth to your feet, okay, your distance is immaterial, right? So this turns out to be approximately the radius of the Earth, right? Okay. So when we figure out the force of gravity on you, let's just do that quick. Let's see if we can find out the force of gravity on you. All right? So what do we need to know in order to figure out the force of gravity on you? We need to know the radius, for one, and we need to know what G is. Anybody remember what G is? Get out your constant sheets and find it.
It's 6.67 times 10 to the negative.
There you go. Let's see if we can find the... Here we go. Radius of the Earth.
I've seen his negative 22.
Okay, first of all, big G equals 6.67 e to the negative 11th Newton meters squared per kilogram squared. Is that right? Okay, the radius of the Earth. The radius of the Earth is 6.38 e, or times 10 to the 6th meters. Okay? Times 10 to the 6th meters. All right? All right. Oh, we need to know the mass of the Earth, right? Goodness gracious, more stuff to figure out. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And what's the mass of YOU? Anybody know what their mass is in kilograms?
It's practically half the foot.
Yeah, it's about
2.2.
it's about half your weight. If you take your weight in English pounds and divide it by 2.2, here, let's say 75. Make it easy. About 75
You know what's easier? 100.
kilograms. Yeah, 100 would be easier. All right, everybody got your calculators. Let's figure out the weight of this person. Okay, who doesn't have the calculator yet?
Yeah.
Negative 734 point.
Negative 730.
0.9?
Yes.
Okay, we have 2 sig figs here. We got 3 sig figs here, so let's just round to 3. Here, 75.0, how's that?
Now I'm happy.
Are you happy? All right. So negative 735. Now I'm walking around. I see several of you doing this. You're typing in your calculator 6.67, and you're doing like the little caret thing, to the negative 11th or something. Okay.
Just use E.
Don't do that. Okay. Use the second EE button. All right. Use the exponential notation. Okay. If you use scientific notation, it makes life much easier on you in the long run. Much, much easier. You can actually work it this way, but sometimes this will get you into trouble. Because you have to put in parentheses and all kinds of craziness. Okay? So, if...
6.67 times 10.
Oh, yeah, that's right. Times...
10.
Yeah, you got to do times 10 caret negative 11. It's way, way more keystrokes. Then you got to put parentheses around the whole thing. Okay. Remember to use the second key and then use the EE key. And then you would put in the negative, and you'd put in 11. All right? So it's faster in the long run. So if you're having trouble doing this or you never learned how to do this, let me know and I'll show you. Okay? I'll show you how to do it, or have someone else show you if you don't want to have me come by and show you. Okay? All right. 735. That's the force of gravity on this person of 75 kilograms. Okay? What's the, remember from last year, force of gravity? What unit is that? That is a Newton, right? A Newton of force. But wait a minute. Wait. Force of gravity is, that's your weight, right? How do you figure out your weight? You remember? It's just m times g, right?
Yeah.
So what's the mass of the person? 75.0. What's the g? On Earth, it's about 9.8 meters per second squared. So what do you get? 735. Oh, man. All right, so we've learned several things here. What did we learn?
So we all that work to wait.
Yeah, we did all this work for nothing. No, we didn't do it all for nothing. We learned that the force of gravity is your weight. We've learned that on the Earth's surface, it's much easier to figure out your weight or the force of gravity by doing this, right? But think about it in a bigger picture. We've learned something else.
F equals mg.
Very good. This equals mg. Okay? It's going to come in real handy later. This equals mg. But wait a minute, which m is this? Is that the mass of the Earth or of you? That's the mass of the person, right? Y-O-U. This is Y-O-U. And this is the mass of the Earth, right? So wait a minute. That and that cancels out, right? So what is G equal to?
G.
Negative G, big M.
And this is the radius of the Earth squared, right? Or the radius of the planet squared, right? So I'm going to get rid of that. So you can find out. Now I dropped the negative sign. I'll talk about that in a minute. You can find out G. And what's little g again? Okay, it's 9.8 on Earth, right? But what is G in general? Little g. Not the gravity of the planet, but the acceleration because of gravity. Okay, it actually also is what we call the gravitational field. Okay, so you can find out the gravitational field or the acceleration due to gravity on any planet if you plug in big G. Does big G change from planet to planet?
No.
Okay, that's a constant, right? That you just look up on your constant sheet, called the universal gravitation constant. So that's constant everywhere. This is the mass of the planet, and this is the radius of the planet. Okay? So like for instance, if we had, planet X, and planet X has twice the mass of Earth and twice the radius of Earth, will you weigh more on planet X? Or will you weigh less? Or will you weigh the same?
Less.
You weigh less.
Because it's the
Because
radius.
the radius is
More.
squared.
Oh wait,
The radius is
If
squared.
you double the mass on planet X than Earth, and you double the radius, but the radius is squared, right?
Yeah.
So what happens to
You weigh
the...
less.
Yeah, you'll weigh half as much. In fact, if you fall out of a tree, you'll accelerate towards the surface of planet X at only half the rate, right?
So we float.
Doesn't mean you float.
It just means it's a longer.
It just means you have longer to think about it on the way down.
So it's like slow motion. Like.
Yeah, it would be like slow motion, and you'd hit the ground with less speed, right?
Less damage.
So it'd be less damage, that's correct. So if you were playing basketball, here we're in baseball season, if you're playing baseball, how would the game of baseball be different on planet X?
It's like a lot of food ball.
Got it. It would be really hard because everybody could run a lot before. Hold on.
That's right, a pop fly you could, well, and also think about it for this, yeah, pop fly would take forever, right? Waiting, I'm waiting.
Have your text later.
But also, what about this? What if you hit the ball?
Oh,
It'll go a lot further, right?
Yes.
Because gravity on that planet X will be pulling it less, so it'll go a lot farther. So you might need 12 outfielders, right? Because the outfield would be really big, right? Of course, in the outfield, you could heave a ball a lot further in towards home as well,
Oh
right?
wait, but why would you need more outfielders if it's way bigger? If you can move.
These.
But no. What I'm saying is, if the ball's coming down
he's
super
going
slow,
all
why would you
about
need more
since it's so
outfielders?
slow.
Oh, good
That's
point.
what I'm saying. Like they
Good
can cover
point.
more ground in this time.
So on Earth, it looks kind of like this, but on planet X, you might need like that, so that you wouldn't have every hit being a home run. A pop fly going out.
What is that ball field?
They could play on a football field. Our equation for gravity tells us that your location makes all the difference. So why is it that we can use mg for gravity? Force of gravity equals mg. We can use this on the Earth's surface, but we can't use that when we get farther out.
Why is it you say?
Yeah, why?
Because the radius will start changing. The radius will be different, so then it's not just the radius of the Earth that matters, it's the radius of the Earth plus the difference between you and the ground.
Because this g equals, what does it equal again? Big G? M over r squared. So like when you're near the Earth's surface,
It's not significant.
do you notice that when you're near the Earth's surface, if we climb a 10-story building, the radius from us to the center of the Earth doesn't change much? So that this little g stays about 9.8. And so that means it's still the same equation, right?
But once it becomes significant.
Yeah, once it becomes significant, like if you climb to the top of Mount Everest, your weight changes. If you take a bathroom scale up there and stand on it, on the top of Everest, and you stand on it in Death Valley, you'll weigh about 1% or so different. Okay? Still not very much, right? So we assume it to be almost the same. Now, when you get a person out here, this radius varies. So g is no longer 9.8 at that spot. And so therefore we can't use this anymore. Does that make sense?
Yeah.
Okay. All right. So, but why is this a conservative force? Okay, this is a conservative force because of this location. Okay? Any force that is a variable of location, or the location makes a difference for what the force is, then it's called a conservative force. There is another one. Electric force. Electrostatic force. Can you remember what that equation is?
K.
Okay. Q1, Q2 over R squared. Okay? And hey, look at that. Location makes all the difference in the world again, right? You could do another one of these for magnets if you wish. All of you as children somewhere along the line have played with magnets, right? Okay. You know that the closer you get the magnets, the bigger the force is, right? And the farther away the magnets are, the weaker the force is, right? Same thing. All right? There's another one. How about spring force? Spring force. Do you remember that equation? F equals
1/2 KX.
KX, 1/2.
not 1/2. It's just
Wait, what?
minus KX. Remember that from last year?
Oh, the force, yeah.
Yeah. Way back. All right, that's your spring force. And where is the location on this one? Right here. Okay? All right. Any force that has a location in it is called a conservative force. Okay? And the reason why it's called a conservative force is because it doesn't matter how you get from one place to another place in that force field, it takes the same amount of work to get it there. Like for instance, if we have a person, they're right here on the planet, and we want to get them to this location right here in space. Okay? If I take them and move them from here to here, it takes a certain amount of work to get that done. Actually, it turns out that if I took them and shot them over this way, and then this way, and then this way, it would be the exact same amount of work. Or if I did it this way, to get them there. It wouldn't make any difference. It would be the same total amount of work to get them there. Okay? All right. Because the force only depends on location. It doesn't matter what the path is to get there. Now there are other forces that where the path makes all the difference in the world. Like for instance, these are called dissipative forces, and one of them is called friction. Okay? You remember the equation for force of friction? It's all right. It's equal to the normal force times, actually it's usually written this way, mu times the normal force. Now I really don't care if you remember right off the top of your head what all those things mean. This is the coefficient of friction, which is essentially how rough the surfaces are. And this is the force that pushes the surfaces together. Okay, like for instance, okay, take your hands, put them together. Okay, now rub them. Feel the friction? Okay, now, no? Okay, now push them together. Push them together hard, and then rub them together. You feel the increased friction. Now, have you changed the surface of your hands? Okay, the surface of your hands determine the coefficient of friction. All right, if you would coat your hands with baby oil, or like talcum powder, something that's slippery, then the coefficient of friction would go down. If you coat your hands in sandpaper, then the coefficient of friction goes up, right? And this is how hard you push them together. Now look, there's no location here. There's no X, there's no R, there's no location. So tell me this. If you're pushing a box, okay, from this location to this location, will it take more work to travel path A, or to take it and push it all the way down here and then around and then up to here along path B?
It would be less. A would be less than B.
A would be less, because the path makes all the difference in a non-conservative force. It's like if you're going to push a piano up a flight of stairs, okay? All right. How you push them up, or which path you take to get them from the first floor to the second floor, makes all the difference in the world for how much overall work it takes, because you're sliding it across the floor, right? However, if you're just lifting something up, like for instance, if I'm taking this and lifting it from here to here, if I do that, or if I take it and go like this, go like this, and go like this to the same spot, in physics, that's exactly the same amount of work. Air friction. Dissipative force. Drag is another one of these dissipative forces. Okay? There are a bunch of them. Tension, normal force, a whole bunch of these. All these that don't depend on dislocation. But these are the ones that will pop out the biggest for us. Okay? Alright, so here's the deal. Dissipative forces, when these act on an object, these forces will create thermal energy. Okay? Think about that for a second. When you take your hands and you rub them past each other, you create thermal energy, right? If you take your hand and lift it from here to here, now you've done work by lifting your hand, but you didn't make your hand any warmer, did you?
Not much.
Not much, right? But you gave your hand energy. What kind of energy did you give it?
Gravitational.
Gravitational. Okay. If you do work against these types of forces, or if these do work, then instead of them giving you thermal energy, what do they give you instead? They give you a type of potential energy. All right? So every conservative force there is a type of potential energy associated with it. Okay? Every dissipative force that there is, like normal force or tension or friction or drag, any of those types of forces, they will create thermal energy. Okay? Does that make sense? So like if you take, your car is rolling down the highway. You take your foot off the gas. It's rolling down the highway. When it's rolling down the highway, what kind of energy does it have? Okay. A little slow, but it's all right. When your car's rolling down the highway, what kind of energy does it have? Kinetic, excellent. And it's rolling down the highway and eventually comes to a stop. What's happened?
Oh,
If it's along a horizontal surface,
horizontal.
has its potential energy gone up or down? Its kinetic energy's gone away though.
Because it used the energy.
Where'd it go?
It went through the friction and
Friction and air drag did work on it, right? And turned that kinetic energy into what? Thermal energy. That make sense? All right. So, one of the things about energy that we find is that energy does not just magically disappear. Now, energy has a lot of magical qualities. Energy can transfer from one object to another, or from one place to another. And energy can change from one variety to another variety. Like kinetic can change to potential, and potential can change to thermal, and you can even get thermal to change to kinetic and potential, although we'll talk about that. It's a little harder to do. Okay? But the energy won't just magically go away. All right? So it has to go somewhere. All right? So as far as we know, the energy of the universe is staying exactly the same, as far as we know. All right. What about black holes? It's still got to stay the same. All right? Even with black holes, the amount of, well, okay. When we get into modern physics, we find that matter, you remember in chemistry class? Chemistry class, you have a law called conservation of mass, right?
Yes.
We're in a chemical reaction, the mass before and the mass after has to stay the same, right? Okay, and in here we talk about conservation of mass a little bit, and we talk about conservation of energy, right? As we get into modern physics, into quantum physics, we find out that mass and energy are two aspects of the same thing. And so we end up with a bigger law eventually that says that the energy and mass before equals the energy and mass afterwards. Okay? So like it's possible for objects like in nuclear reactions, they will lose mass and the mass disappears and turns into an equivalent amount of energy. Okay? It's like you have lots and lots of energy even though you're sitting there and you're hungry. All right? Hungry for lunch. Because everybody knows this equation. E equals mc squared. If we just take your mass and plug it in here, and c is the speed of light squared, which is a really huge number, you have a tremendous amount of energy just because of your mass. Okay? If you could convert all of your energy into all of your mass into energy,
You'd be missing it.
you would disappear, but we would thank you because we wouldn't need oil from the Middle East anymore. Because you would power our state for a long time. So let's see if you understand this. Let's say that you've got a safe here with all your valuables in it. All right, and you're going to move it into this building right here. All right, and you're moving your safe from here to the 3rd floor. Actually, I guess it's the 4th floor, right? So here, along path A, you take it in the door and you take it up the stairs. That's path A. Path B is you build a ramp and you take it right up the ramp into the 4th floor.
what is it?
Or
Lift it.
you do this, you walk it over here and then you throw it into the window. Or you buy a helicopter and you take it up here and you drop it in the window. Okay, in which case, starting from here and ending here, in which case do you have the biggest change in potential energy?
The most kinetic energy.
They're all the same, just going the same.
Well, D goes higher.
We're talking about change in gravitational potential energy, right? Because it begins at rest and ends at rest, right? So that's going to be final. Our change is going to be final minus initial. The final spot and the initial spot are exactly the same, right? You have the same MGH final that you have MGH initial in each case. So the change is the same no matter what. Okay, now this is going to be true of all types of potential energy. How you get from spot 1 to spot 2 makes no difference for potential energy. All that matters is where you began and where you ended. Does that make sense? All right, that's all that matters. Same thing is going to be true of gravitational potential energy in space. Same thing. All right, same thing is going to be true of spring potential energy. Okay? Same thing again. So let's talk about spring real quick. We've talked about these two. Let's talk about spring potential energy. In spring potential energy, you have your spring. I'm going to attach this spring to the wall and have it on a horizontal surface like this so we don't have to worry about any vertical movement. Okay? All right, if I place an object right here, has a certain amount of mass, and I push it this way, okay, I'm going to give this thing potential energy, right? Because if I let go, that stored energy can shoot that thing off, right?
Yeah.
All right, so in this equation, the important things is there's this x equals 0 called the equilibrium position. The equilibrium position is where the forces all cancel out and it will just sit there by itself and not want to move. Okay? So if I compress it this way, which way do you want to call positive? Pushing it or pulling it? That's fine. We're going to call this way positive and this way would be negative, right? You okay with that? Alright, so if we compress it or stretch it, notice that it's squared no matter what, right? So our potential energy for a spring is always going to be either 0 or positive, right? So it's going to be a lot like kinetic energy. Kinetic energy is only 0 or positive. You can't have less than 0 kinetic energy. That would mean less than moving. Less than not moving. Exactly. So there is no such thing.
Actually, there is. We're going into the.
No, stop. Only in your imagination. All right. K is the spring constant. Okay, K is the spring constant, and the spring constant is in units of newtons per meter. So it tells you how many newtons it takes to stretch this thing 1 meter or to compress it a meter. Now, will all springs stretch or compress a meter?
No,
And like some of you that have the ink pen right now, if you take it apart, there's a little spring in there. You're not going to be able to stretch that sucker a meter, right? Or compress it a meter. So you just figure out, it took 12 newtons to stretch it a centimeter. So you just take and convert the units and you get newtons per meter. Okay? No big deal. So that's the spring constant. It tells you the springiness of the spring. All springs are not made equal. Some springs, like the springs on a car, are really big and heavy and have huge spring constants. The spring constant of the spring in your ink pen better not be like a spring in a car. Because then you wouldn't be able to click it. Right? Or you unclick it and it'll shoot the thing apart. Right? Alright, so different spring constants. Alright. So you have positive spring potential energy this way and positive spring potential energy that way. Is everybody okay with that? Excellent. Hey, will you graph spring potential energy versus displacement if you graph positive or if you push it negative? What's the spring potential energy look like? What's its graph look like? A parabola. Why is it a parabola?
Because it's squared.
Because it's a parabola, right? Because it's squared. So the spring potential energy will look like this, where when it's in equilibrium you have 0. So if you stretch it or compress it the same distance, it will have the exact same energy, right? Ooh, that brings up an important point. What if I put you against the spring like this? A great big spring. All right? So here you are, just like this. And I attach you to this spring. And I stretch you all the way out here.
Oh, God.
And then I let go.
Who would be happy?
So if you start out here,
Into the wall?
Well, not into the wall, but
what's going to happen? You're going to have all of this spring potential energy out here, right? And then what's going to happen to your spring potential energy? It's going to go down to 0 when you're right here. So you have lots of spring potential energy, and then it's 0.
You keep going.
Why?
Momentum.
It's momentum.
Oh, there's lots of ways to explain it. One is momentum, because you're already moving, and is there anything to stop you here? You're in equilibrium there, right? Which means no net force. Come on. We need lunch. We need it now.
Let's go.
All right, so you're still moving, and there's no force right here to stop you, right? So you'll overshoot. Okay, so, or you could say, well, my spring potential energy has converted into kinetic. Stop it. Kinetic, right? So now you're moving. So you're going to keep shooting this way. Till when?
Until you
Until
convert that,
until the spring is enough to not
until
make
you
it
convert the
go
kinetic
back.
into
Okay, you could say until the force is large enough to stop you
And then
and return you back. Or you could say until
momentum.
you're back to,
when you convert kinetic back to the spring.
yeah, until your kinetic converts back all into spring, and then you've stopped, right?
Well, that's
And where will that be?
that's assuming
Well, in a perfect world, at the same spot.
In our nice, perfect physics world of
no friction.
perfectly uniform springs and no friction, then you would go exactly to the same distance beyond equilibrium that I stretched you beyond equilibrium on the other side. Does that make sense? And in our perfect imaginary world of physics, you would oscillate forever, back and forth between those spots. Now, does that happen in our macro world of physics? No. Does it happen in the micro world of physics? Yes, that happens all the time. Because on the atomic scale, this happens all the time. But it happens not because of springs, but because of the electric force. Think about it this way. What if I had a positive charge here and a positive charge here, and I put a negative charge right in the middle? Okay, would it be pulled both ways the same? If I have a proton, and an electron? Sure. So what if I take this and I push it over this way? What's going to happen now?
It's gonna move towards the other.
It's going to move towards this side because it's closer to this proton, so it's going to be repelled more, right? But when it...
It's an electron.
I'm sorry. This electron will be repelled from this one more than it's repelled from that one, right? So it's going to shoot to the right.
that's right.
Oh!
Yeah. You really need your lunch.
Okay, let's erase this from the tape. All right. We put a proton here.
Bloopers, right?
Yeah, that's the blooper reel. All right, so we take this one and we put it over here. I'm going, why are you all saying it's going to try? All right, so you put it right here, and it's going to repel that way more than it repels this way, right? So it's going to repel to the right. But when it gets to the center, it's in equilibrium again, right? All the forces cancel. So it's going to keep going. It's going to overshoot, right? And when it overshoots, guess what? It's going to go over here
Same distance.
the same distance x. And it will actually oscillate back and forth. Forever.
Until somebody actually kicks that.
Yeah, until Heisenberg comes along and we don't know exactly where those protons are and something weird happens, right? All right, but this sort of thing actually does happen in the atomic world or the subatomic world, okay? Because there's no such thing as friction down that small, okay? All right. So we have electric potential energy as well. And the electric potential energy, you notice that this equation right here matches that equation really nicely, except for the negative sign. The negative sign means that we're always going to be in attraction mode, whereas this one, you can either attract or repel, as I found out. Depending on whether you have positives or negatives, right? Okay, so here's the deal. As long as you don't have dissipative forces, okay? As long as you don't have any forces that will cause thermal energy to be created, then your kinetic energy and your potential energies will all add up to be the same all the time. Because remember I said the first day that work is the transfer of energy from one place to another, right? So if there's no work done by these things, okay, creating thermal energy, and there's only work being done by these types of forces, and we think of them in terms of their energy instead of what they're doing with their forces, then all of the energy will stay exactly the same. Okay, and we have what we call conservation of energy. All right? So real briefly, let me start that idea, and then we'll be done. All right. Work. All right. Work transfers energy from one place or object to another. Okay? So, if work transfers or changes the energy, so work can change the energy of a system or object, or whatever it is. So that means if there's no work, then the energy of the system doesn't change. Which means that the energy at the beginning will equal the energy at the end. And that's called conservation of energy. Okay? And that's called conservation of energy. All right? So, we're going to have to worry about what type of forces we have and what type of work they're doing. Okay? So, like for instance, let's see if I can explain this properly. If we have gravity, we have a baseball right here. Okay? And obviously, gravity is pulling this thing down, the force of gravity. Okay? So, is there a force on this object doing work? Sure, it's gravity. Okay, if it starts from rest and this thing falls, what kind of energy is gravity either giving the ball or taking away from the ball?
It's taking away potential and giving it kinetic.
Okay, so it's changing it from potential to kinetic. All right, but if we just think about gravity in terms of its force, we can either think of gravity in terms of the force that it is or the type of energy it's giving or what it's doing energy-wise. So when this falls, it starts from rest, which is kinetic energy equals 0, and it ends up moving. So it has kinetic energy, right? Kinetic energy is getting larger with time. Does that make sense? So the gravity is doing work, giving this thing kinetic energy, right? Okay, or we can think about it in terms of like this. Since gravity is one of our special forces, we can think of gravity in terms of the type of energy that's involved. All right? So we could say, what kind of forces do we have acting on the ball? Only gravity. It's a conservative force. So we can think of its effect on the ball in terms of the type of energy it gives the ball. So instead of thinking of gravity as a force, we think of gravity as a type of energy, or the energy it gives it. So what we end up with here is, instead, we think of Well, there's no net external non-conservative forces. Okay? I know it's a big, long statement, but no net external non-conservative forces. So all we have is gravity. Gravity's a conservative force, right? Assuming we don't have any air drag or friction. Then we can think of gravity as the type of energy it gives, and we start with potential energy, and as it falls, it converts into kinetic energy, right? And that the total energy of the system stays the same, right? Now we can do that for any conservative force. As long as all we have over here is non-conservative forces, the work done by non-conservative forces is 0, then the energy of the system will stay the same. It's okay to have gravity, spring force, electrostatic force, and other conservative forces, and we'll still have conservation of energy. What if we have something like friction then? Will the energy of the system stay the same? Only if we consider thermal energy involved, right? Because yeah, if we consider thermal energy, like for instance, I push the box across the floor, then I'm going to have to include thermal energy in our problem, right? Or you would just say that the mechanical energy, these types of energies, is not staying the same. Does that make sense? All right. We'll start working problems like that on Friday.